Yeah, okay. All right. Sorry about that. Yeah. Yeah, so this was the prediction, okay, the prediction for the liquid to crystal transition. And it's quite remarkable that as better and better experimental realizations of this problem appeared, basically cleaner 2D systems, it looks like this prediction is actually more or less correct. So there is a transition between the liquid and the regular crystal somewhere between 30 and 40. Okay, so what I'll talk about here is basically building on this old problem of the 2D electron gas and discussing new correlated 2D electron gases that have slightly richer properties, if you like, one step up in complexity relative to this classic problem, and they give rise to new phenomena. So what I talked yesterday about these graphene systems, and I'll discuss a simple, what I view as a simple test case, something in many ways simpler than these graphene systems I've discussed. In particular, a 2D electron gas, which also has two valleys and two spins, which is realized in the aluminum arsenide quantum wells, which shows some slightly richer physics than the 2D electron gas. I'd like to advertise that as sort of a simple test case to start building our understanding and our intuition about what these systems do. Okay, so a novel correlated 2D electron gases. Okay, so one such example is twisted bilayer graphene that you heard about. Okay, so the prediction was if you take two layers of graphene and twist them just right, you get these very flat electronic bands, and there's some surprises that emerge. And another such system that I discussed yesterday is a crystalline multi-layer graphene, rhombohedral multi-layer graphene. It shows all sorts of symmetry-broken phases and superconductivity. And there are also multi-layer 2D materials that also shows a strikingly rich set of phenomena. Okay, so relative to the classic 2D electron gas, what's actually different about these systems? These are also 2D electron gases with a small density of electrons and strong interactions, if you like, in some intermediate RS regime. What's different about them is that the electronic dispersion is more rich. Okay, so the Coulomb interaction, long-range Coulomb interaction, is present in all these systems, but the electronic structure has multiple values. The dispersion is not just p squared over 2m, it's anisotropic. Some of these systems have a Moiré superlattice, and there's a very curvature that plays a role. Okay, so the bands themselves are not trivial. The wave functions of the bands are not trivial. And as a result, they show this shockingly rich phenomenology, including both spin and orbital ferromagnetism, multi-insulators, superconductivity, and even integer and fractional Chern insulators, anomalous Chern insulators that appear without a magnetic field, and so on. Okay, and all is coming from the interplay of the same Coulomb interaction with this richer electronic dispersion. What I'd like to do in most of these talks, most of this talk, is kind of build in this complexity of the electronic dispersion one step at a time. And I'd like to imagine, instead of a single valley isotropic dispersing to the electron gas, this kind of system, suppose we have a system that has C4 symmetry, so think about the underlying square lattice in 2 dimensions, and it has two valleys that live at the x and the y points of the Brillouin zone, basically at pi 0 and 0 pi. And consequently, the dispersion of each one of these valleys doesn't have to be isotropic. Okay, so the effective mass in the x and the y directions could be different, but the two valleys are related by C4 symmetry. So if there's one sign of the anisotropy for one valley, it would have to be opposite in the other valley. Okay, so that's the system. This is the dispersion. Two valleys, two spins, anisotropic dispersion in this way. And interestingly, there is actually a good realization of this type of problem. Okay, so this is a semiconductor, aluminum arsenide. This is in 3D, it actually has three symmetry-related valleys. But if you thin it to a quantum well, only two of these cross the Fermi energy. Okay, so you get exactly this kind of electronic structure. And this type of quantum well has been perfected by Mansour Shagan's group from Princeton. Okay, they know how to make these 2D electron gases with very high mobility. And interestingly, the effective mass in the system, if you compare it to gallium arsenide, the effective mass m star, which is the average, the geometric average of the two masses in the x and y directions, is much bigger. Okay, which in particular that means that you can reach the interesting regime of large RS already at higher densities. Okay, you don't need to go to as low densities, which means that disorder plays a reduced role in these systems. So they're good for standing correlated electron phenomena. And moreover, in these systems, the anisotropy, which is the ratio of the effective mass in the x and y direction, basically how eccentric the Fermi surface is quite large. Okay, so it's the order of 5. So these Fermi surfaces are really elliptical, really eccentric. Okay, so yeah, so that's aluminum arsenide. Okay, and what we'd like to understand is,
quick question.
Yeah.
Why would disorder play a smaller role in higher density?
Yeah, so that's because the electrons screen the disorder. Okay, and this the screening is better the higher the density. Yeah. Okay, so right. Okay, so it turns out that this material indeed does something interesting as we scan RS or scan density. Okay, so at large RS, so this is an experiment from the Shagan's group. At large RS or small RS or high density, it's just an isotropic fluid. Okay, so what's plotted here is the ratio of the resistivities in the two principal axes along x and along y. If the symmetry between x and y is not broken, we should expect that the resistivity should be equal. Okay, and that is the case at high density. But you see that at a certain density, all of a sudden the resistivity becomes anisotropic. Okay, so the resistivity in one direction is suddenly smaller than the other, and this corresponds to an RS value of close to 20. And as you decrease RS even further, ultimately the system undergoes a metal to insulator transition. Okay, and there's some interpretation here where we should think about this insulator as a Wigner crystal and when we shouldn't. Okay, I won't go into that, but this all happens close to 30. Okay, so this is RS equal 30. So quite a bit before we get to the metal to insulator transition, the system breaks the rotational symmetry. Okay, and this can be actually investigated further by applying strain. Okay, so if you don't apply strain, ideally the system should be exactly symmetric between x and y, but you can break that symmetry explicitly, analogously to how you apply a field to determine the direction of magnetization in a ferromagnet. Here you can apply strain, and you can actually control which direction by applying strain. You can control which direction has the large and which direction has the small resistivity. Okay, and what's believed to happen here? Okay, what is the cause of this resistivity anisotropy? The interpretation, you can say where that's coming from, but the interpretation is simply that the system valley polarizes. So instead of filling both of these two valleys symmetrically, beyond a certain density, all the electrons just go to one valley. Okay, and why is that happening? Well, in some way, it's simple. It's just analogous to the Stoner ferromagnetism that you expect for the spin. Okay, so to minimize exchange energy, what the electrons can do is just go all to the same valley instead of to the same spin. Okay, that minimizes exchange energy at the cost of an increased kinetic energy. And as the interaction become more and more important, this is something you might expect to happen. Of course, the question is, why valley polarized and not spin polarized? Okay, so you have another option, which is just to polarize the spins as in a ferromagnet. That would achieve the same gain in exchange energy. And second, in the isotropic electron gas, for a long time it was believed that it should become ferromagnetic, spin ferromagnetic, before it actually goes into a Wigner crystal. That turns out to be not the case. Okay, so the energetics is such that the system crystallizes before it has a chance to spin polarize. The metallic phase is apparently never spin polarized. What is special about this system? Why is value polarization so much favored over spin polarization? Okay, so that's what we'd like to understand. And similar physics in a different guise appears in these graphene systems. These are also multi-valley systems with anisotropic dispersion. And we saw this richness of phase diagrams you can get there with interplay between different symmetry-broken phases. In a way, this for me, this is a kind of toy problem to start to understand that much more complex problem. Okay, so as a theorist, what we like to understand is map out the phase diagram of the system. The isotropic electron gas had only one parameter, which is Rs. Here we have two parameters. Okay, so we have both Rs and eta, which is the mass anisotropy, the ratio between the effective masses in the x and y directions of these two values. So we'd like to map out these this two-dimensional phase diagram. It would be useful to add a third axis, which is a screening axis. Okay, so the problem we're interested in has long-range Coulomb interactions. There's a third axis we can imagine, which is basically a distance to nearby metallic gates. Okay, so this is our 2deg, and we can screen the long-range part of the Coulomb interactions by having nearby metals. Okay, so that leaves the short-range Coulomb interaction more or less the same, but the long-range Coulomb interaction is screened. In the actual experiment, there is a gate only for one side, but it's quite far away. It's probably not so important. So in this parameter d, which is the distance to the gate, here I'm plotting 1 over d. We're somewhere down here. Okay, so the distance to the gate is very large. The interactions are long range, but it would be useful to imagine, to ask what would happen if the gates were closer and closer, and the interaction is more and more screened. Okay, so in the other extreme limit, the interaction is really point-like. Okay, so now what can we do? Okay, so at large RS, we sort of know that this mass anisotropy shouldn't matter. Okay, for large RS, interactions are very strong. We don't care about what the kinetic energy is anyway. We want to just minimize potential energy, and we'll get some kind of Wigner crystal. We can try to approach the problem from the weak coupling limit, from the other extreme limit, where we can expand in RS. Maybe we can understand something. We can approach from the strong interaction or large RS limit and do a strong coupling expansion. We can access the dilute limit, where these gates are very, very close. This point interaction simplifies the problem somewhat, and try to expand there. But ultimately, the experiment is done in the regime which is hardest, which is intermediate RS and long-range interactions. And there it will resort to numerical techniques, basically variational Monte Carlo, and we'll try to gain some understanding from combining these different limits together. Okay, so that's what I want to do. I'll start from the Monte Carlo. Okay, so yeah, just before that, let me just write the Hamiltonian. Okay, so this is the Hamiltonian. Here's the anisotropic effective mass, and there's a Coulomb interaction, which is long range. Okay, this thing is just the Fourier transform of a screened, of a gate-screened, dual gate-screened long-range Coulomb interaction with a gate distance of d and the dielectric constant of epsilon. Tau here is the value index. Either plus or minus 1 determines these two values, and there are also two spins. Okay, so it's a very simple Hamiltonian. There's some effects that we didn't include here. Okay, so no phonons, no electron phonon coupling, no spin orbit coupling, which is believed to be weak in these systems. We took into account only the long range part of the Coulomb interaction. That is to say, we neglected inter-valley scattering. Okay, so this picture is not to scale. The electron density is very, very small on the scale of the area of the lattice constant. We assume that the interaction that scatters an electron from one value to the other, that happens at a very large momentum transfer. Because it's Coulomb, it decays like 1 over q in 2 dimensions. So that's very small compared to a small momentum scattering, which leaves you within the same value. Okay, so that part we neglected. We expect that to be small. We kept only the biggest terms in the Hamiltonian, and this is what they are. Okay. All right. So just as a warm-up, I'd like to show the results from Hartree-Fock mean field theory. Okay, we don't expect Hartree-Fock to work well at all, and it doesn't. But nevertheless, there's some interesting lessons from doing that. It's very simple. So that's the first one. That's the first thing one does. Okay, and this is the phase diagram. So this is a Hartree-Fock calculation. The axes are the same as before, basically RS and the anisotropy parameter. Okay, and what you see here is the different phases that one finds. Okay, so when RS is small, this is the symmetric Fermi liquid phase where all the spins, all the values are equally populated. And then you have this cascade of transitions. First, you fill only 3 of the 4 flavors. So you pick 3 flavors, spin or value polarized, and fill these. And then you have a phase where only 2 flavors are filled, and then finally only 1. Okay, and we didn't include the crystal, but in this calculation, but ultimately the system would actually crystallize.
So your Hamiltonian at this point has, it looks like from this phase diagram, has the full like kind of symmetry of like spin and value are basically really on the equal footing.
So let me comment about that. So it's an important question. So the symmetry of the Hamiltonian is there's a discrete symmetry that relates the values. Okay, you can rotate by 90 degrees. That's actually the physical symmetry of the Hamiltonian. There's an additional symmetry, which is spin rotation, but you can actually rotate the spin of the 2 values independently. And that's an artificial symmetry. That's because we didn't include this large momentum scattering from one value to the other. Okay, so I'll say a word about what that means in a moment. But spin and value are not equivalent, the Hamiltonian level, because of the mass anisotropy. Okay, so there's no SU4 symmetry. Okay, that's going to be crucial. Okay, so so where does that hit us in the face? So good. This one stopped working, so maybe I can use just here.
One quick technical question.
Yeah.
If F is equal to 1, do you still see a phase which you label as 3?
Yes.
Really?
This line is eta is equal to 1. This is with long range Coulomb.
Coulomb interaction.
Coulomb, yeah.
Because with short range interaction we never see.
Yeah. This is Coulomb. So with Coulomb we do see it. Yes. Yeah. Okay. So So look at something. A few comments. Okay. So one comment is that as one may expect, Hartree-Fock vastly overestimates the stability of these symmetry broken phases. Okay. You start getting symmetry breaking when RS is a order 1, it's close to 1. Experimentally, they only see the value polarized phase when RS is equal to 20. But even at the more qualitative level, this phase diagram is off. Okay, first of all, there's the threefold phase, which is not there in the experiment. Okay, but second, more interestingly, okay, in this phase where you choose 2 out of the 4 flavors, there's a degeneracy between spin and value polarization. Okay, so within Hartree-Fock, you get the same energy whether you fill one value with both spins or you fill one spins with both values. And this is an accidental degeneracy. Okay, so that's this is not a symmetry of the Hamiltonian. But within Hartree-Fock, there's no way to distinguish these 2 states because the exchange energy is exactly the same. Okay, so we expect a more accurate calculation to lift this degeneracy somehow in favor of either spin or value degeneracy. Okay, and finally, there's an interesting thing which is not apparent in this phase diagram. It turns out that when you do Hartree-Fock, you look for the best Slater determinant state, and the best Slater determinant state does not have a dispersion that corresponds to the bare anisotropy. The anisotropy itself is renormalized by the interactions. It turns out that exchange interactions don't like this very elongated Fermi surface. Think about it, it's a little bit like surface tension. It kind of likes to have circular Fermi surfaces instead. So you get that the anisotropy is renormalized down. And sometimes this is an extreme effect. The actual anisotropy of the Fermi surface that you get within Hartree-Fock can be much smaller than the bare parameter. All right, so we'd like to do better than this. Okay, we know Hartree-Fock shouldn't work when RS is large. So what do we do? Okay, so we resort to this technique developed among other people by separately of variational Monte Carlo. Okay, so what we do is simply we write down a wave function that's supposed to capture correlation effects beyond Hartree-Fock, and that wave function would have some number of parameters, and we minimize the energy over these parameters. Now we can't calculate the energy exactly, so we do that by Monte Carlo sampling. Is the name, and this is the ansatz that we'll use. Okay, so the answer is a Slater determinant using Hartree-Fock multiplied by a Justo factor. Okay, so this is the function of the coordinates of the electrons that makes the wave function vanish when two electrons are close to each other. So this is capturing correlation effect that we expect the Coulomb interaction to have. Okay, so the Justo factor in practice is the sum of pairwise functions, functions of pairs of coordinates of two electrons, and it just goes to zero in some rate when the two electrons are close. And beyond that, there's also what's called a backflow transformation, which means the following: the Slater determinant is not evaluated at the physical coordinates of the electrons. It's evaluated in some slightly modified or shifted coordinate that depends on the position of all the other electrons. And what this represents, if you have the electrons in some given position, it tends to push every electron slightly off its position in the Slater determinant. Okay, so hence the name backflow. Again, why is this important? If you think about it, if you didn't have this backflow and you just evaluated the Slater determinant at the actual positions of the electrons, the position of the nodal surfaces of this of the wave function that you write would be identical to the position of the nodal surfaces of the Slater determinant. Okay, so this is a fixed node that's too rigid in ansatz. To be able to move these nodes, you use this backflow transformation. Okay, so this is effectively moving the nodal surfaces of the wave function around. The Justo factor alone doesn't do that. If you like, it doesn't change the phase of the wave function. It only changes the amplitude. And this turns out to be important in some of the energetics that I'll show. Okay, so this is the wave function that's used for the liquid in the same kind of variational Monte Carlo calculations I've shown before, that for the isotropic electron gas predict the transition at Rs equals 30 between the liquid and the solid. Okay, this is the phase diagram that we get this calculation. So again, Rs this axis and eta the mass anisotropy that axis. The dashed line corresponds to the value we believe is correct for aluminum arsenide. Okay, you see three phases here. Green is the symmetric phase, the symmetry unbroken phase. This blue is a valley polarized, spin unpolarized phase, meaning all the electrons go to one valley. And this yellow is a spin and valley polarized phase, where you only occupy one spin in one valley. Okay, so several interesting things here. First of all, when eta is equal to 1, you basically get no symmetry breaking all the way to Rs close to 30. Okay, where we actually believe the crystal should be. We haven't included the crystal in this calculation, so we wouldn't know. But presumably that means the system just never polarizes in any channel. Okay, but something really interesting happens when you start making the dispersion more and more anisotropic. So you see that these symmetry broken phases really start occupying more and more of the phase space. And in particular, okay, for the aluminum arsenide value of close to 5, we get a transition between the symmetric phase and the valley polarized phase close to Rs equals 12 in this calculation. And in particular, the range of this valley polarized spin unpolarized phase expands as we increase eta. Okay, so this is not quite the right value in experiment. In experiments, it's 20, not 12, but at least it captures some of the correct physics. The value is not so off. We don't get this intermediate threefold phase. We get a direct transition from the symmetric phase and directly into a valley polarized and unpolarized phase. And we actually think we understand what was missing even to push this transition even further. Yeah. 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 So what people do for it's an interesting question. Within this technique, to capture the Wigner crystal, you actually need a different wave function. Okay, you just compare energies. This wave function is not flexible enough to describe the Wigner crystal by itself. Okay, there's some the transition within these calculations is fifth order. Yes. By the way, all these transitions are also fifth order. Yeah. Yes. how do we know? Yeah, so we know a little bit indirectly. So they look at the dependence of the resistance on in-plane field. Okay, so the idea is if you're becoming if you're getting close to a ferromagnetic transition, what you should see is that there's a very big splitting between spin up and spin down, and you should see that in a magnetoresistance for the in-plane field, and that saturates where you have full polarization. And that's not seen in this part of the phase diagram. It is seen close to the insulator. Okay, so there it is believed to be spin polarized. The best thing would be Shubnikov-de-Haas oscillations, but we haven't gotten that in this regime. Yes, yeah. Okay. All right. Yeah, but the latest calculation definitely it's not spin polarized in this regime. Okay, so the question is, how do we understand this? Okay, so this is the result. It looks in many ways encouragingly similar to the experiment. What's the reason? Why does anisotropy favor so much the valley polarized phase? Why doesn't it in fact favor the spin polarized phase? Okay, so yeah, before I go into that, a couple more comments about this calculation. So first of all, here's the energetics that went into this phase diagram. So these are the energies of the different phases. Okay, a reference to the symmetric phase. So this is the energy of the valley polarized, spin polarized, and spin and valley polarized phase. Also some partial polarization to be considered as a function of either Rs at a fixed eta or as a function of eta for some fixed Rs. Okay, so as you increase Rs, as you expect, okay, the valley polarized phase goes down the most rapidly, and this is the first order transition between different phases. And here you see the energetic competition as a function of Rs. Okay, so this is the region of stability of the valley polarized phase. The thing which is striking with this diagram is this is the difference in energies in millivolts per electron. Okay, so just as a comparison, the typical Coulomb energy per electron is a few millivolts in this regime, and you see these tiny energy differences that actually determine the competition between these different phases. Okay, so this is really striking that the valley polarized phase wins, but not by a lot. It's really quite subtle energy differences that determine this. This is quite typical in correlated electron systems that you have competing phases which have small energy differences, and they're all kind of almost on equal footing.
How robust are these conclusions to the ansatz?
Yeah. So right. Yes. So that's a good question. So first, these small energy differences makes one worry. Right? Makes one worry that indeed you have to have a very good accuracy, meaning a very good ansatz. Yes. So similarly here, right? You can predict the energy very precisely, but with the order totally wrong. So so we tested that to a limited degree. Here, for instance, one can ask about the spectral transformation, how important that is. And for the basic conclusion, that's actually not so important. So for the fact that valley polarization is favored, you get that even without using backflow. Just the Jastrow factor is enough for that. For the detailed competition over here between spin polarized and valley polarized, that is important. Okay, so the answer is for some things it is important. Now, what I can say is more another comment to that, more historical. Okay, these wave functions have been evolving for decades, and this value of the Wigner crystal to Fermi liquid transition, which is also very subtle energetics, has wiggled, but it's wiggled between 30 and 40. So, and the basic structure of the phase diagram actually did not change.
So if the difference is that small, does it mean that you raise temperature a little bit and then it's very over the?
Yeah, that's a very good question. Yeah, if you try to translate this into a temperature, this is in a few hundreds of millikelvin.
Right.
Yeah, so the experiment was only done at one temperature, actually not particularly low. It was done at 300 millikelvin. If you try to estimate what the entropic effects at that temperature should be on this phase diagram, they're actually small. These are all metallic phases. So there isn't a lot of entropy, so the phase boundaries may not move so much, but we don't really know. Yeah. Okay. Right. So another quantity that's interesting to look at in these calculations that we have looked at is the anisotropy of the Fermi surface. Okay, so we discussed how within Hartree-Fock we get this very drastic renormalization of the anisotropy as a result of the interactions. And in these calculations, we can just calculate directly the occupation number in momentum space, the n of k, from the wave functions that we get. And you see very clearly that this jump in n of k, which is the Fermi liquid jump. Okay, so this is the discontinuity in the occupation function as a function of momentum. And as one would expect, it's different in the x and the y directions for one valley. Okay, this is actually in the valley polarized phase. And it turns out that the anisotropy that you get from this calculation is modified compared to the bare anisotropy, but not to such an extreme degree as you get within Hartree-Fock. Okay, so Hartree-Fock really exaggerates this renormalization of the anisotropy. Yes. 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 Yeah. That's true. Yeah. Okay. All right. Yeah, so why is this happening? So we'd like to construct some kind of analytical understanding of this, and we can only do that by expanding around certain limits. So we started from the limit of very small RS, weak interactions. Okay, so now when the interactions are weak, the ground state is always going to be the symmetric state. Okay, we're not going to favor symmetry breaking. We saw that symmetry breaking is favored only at quite large RS. But we can still ask the question, which susceptibility is bigger? Okay, what is the system more susceptible to if we apply a small symmetry breaking field, physically either strain or magnetic field? Which is bigger, the spin susceptibility or the valley susceptibility? And which one is growing faster as we crank up the interaction? Okay, now we can't quite reach all the way to the point where the system wants to polarize spontaneously, but we can ask, if you like, which type of order is more favored by the interactions. Okay, and if we just do perturbation theory in the interaction, this is the lowest order term, and this is basically equivalent to doing Hartree-Fock. And this term doesn't distinguish between spin and valley polarization. Okay, so we have to go to the next order with interactions. These are some diagrams that contribute to second order, and tau here is the value index. Okay, so that's continuous across these vertices. It turns out that this term is the first term that actually distinguishes spin and valley polarization. Okay, so it cares whether all the electrons are in the same valley or some electrons that are in valley X, and the other one is Y. Yes. Yeah. So why is the exchange interaction the same for spin and valley? That's the question. Yeah, there's no, the interaction doesn't transfer from tau to tau prime. Okay, so you see that the tau is continuous across this vertex, but why is that? Yeah. So the reason for that is that we've only taken the small momentum transfer, which corresponds to a long range part of the interaction, because it's Coulomb. Yes. Yeah. Yes. Exactly. Yes. Yeah. Okay. So these large momentum transfer, or let me say a word about that. Okay. So these large momentum transfer interactions for Coulomb, first of all, they're small. Okay, they're small by the ratio of the inter-electron spacing to the lattice spacing, which is maybe a couple hundred. Okay, so it's a small effect. On top of that, if you included them, they would always favor spin polarization and not valley polarization. They actually give you the wrong answer. Okay, we can discuss that in a moment, but that's true. Great. Other questions? All right. So yeah. So this diagram, which is the so-called correlation energy, actually favors value polarization. It turns out. Okay. So one can prove. It's very simple to prove. Actually, if you just calculate this diagram, that the energy gain from a second order correlations is always bigger for the value polarized phase. Okay. So it's basically this product of two polarization functions, and if these two polarization functions are the same, you meaning both electrons are in the same value, you actually gain more energy, more correlation energy compared to the case where they're at different values. Okay, so there's a correlation energy gain, and it turns out for long-range Coulomb interactions, there's a log similarity. If you calculate this diagram, the interaction is really long range, you can't stop actually second order, you need to resum. And for small RS, we know that the right way to resum this series is to do RPA. And you can calculate the energy within RPA and basically prove a very similar result. Okay, the correlation energy within RPA is always smaller, always favorable to value polarization compared to spin polarization. Okay, so this is extrapolating the same result to finite values of RS. Okay, so the result was justified, strictly speaking, only at small RS, where neither the ground state is neither spin nor value polarized. We can extrapolate the results to finite RS, just calculating the energies within RPA of the different phases, and this is the result that we get. Okay, so this is the phase diagram. There's a symmetric phase, value polarized, spin and value polarized. The numbers are off. You see that the position at eta equals 5 is 3.5 instead of 12 compared to the numerics, but the qualitative shape of the phase diagram is actually very similar. Okay, so that was weak interactions, weak long-range Coulomb interactions. There's another limit that we can make some analytical progress, which is this contact interaction approximation. So suppose we had metallic gates that are very close by to screen the long-range part of the Coulomb interaction, and we have effectively short-range interactions, much shorter range than the interparticle distance. So this is if you like, this is a dilute limit. Okay, and in this limit, we know what to do. We need to solve exactly, basically, the two-particle scattering problem. Okay, so in this limit, what happens is that because the particles are dilute, only two particles interact at the time, and we can solve the two-particle scattering problem exactly, and use the scattering amplitude as our effective interaction for a new many-body problem that we'll need to solve. Okay, so we can ask about the structure of this two-particle scattering matrix, basically T matrix. Okay, and we can compare the scattering matrix for two electrons in the same valley, the XX, and two electrons in different values, the XY. And you see this, this 1/log factor. W here is the overall bandwidth, mu is the chemical potential. Okay, so we assume that the chemical potential is very small compared to the overall bandwidth. And you get this downward logarithmic renormalization of the interaction that's very typical for 2D. Okay, this is a well-known phenomenon for a 2D system. But what's interesting is that this logarithmic suppression factor of the interaction is actually suppressed for VXY compared to VXX. Okay, and this is coming from the different dispersions of the two values. So this means that both interactions are screened downwards by this two-particle scattering, but the VXY is screened downwards much less, which means VXY is much bigger than VXX in the limit where eta is large. Okay, we can define a particular limit where this anisotropy is big and the system is very dilute, where basically VXY is much bigger than VXX. Okay, and in that limit, two electrons in opposite values repel. Two electrons in the same value hardly don't repel, don't feel each other at all, and we expect a spontaneous value, a polarized state. Okay, so what's going on here? So we got these two limits where we can say something, and both limits actually point to the favor valley polarization. There's a very simple physical picture behind it, actually. Okay, so what's going on here? We have electrons from the two valleys. We have this spatially anisotropic dispersion. Now, if we have strong correlations between electrons, every electron, if you take a snapshot, every electron will just try to avoid the other electrons as much as possible, even though it's a liquid state. Okay, so how do you do that? Well, you want to localize but not pay too much kinetic energy. So if you have an electron from valley Y, and the mass in the x direction is much lighter than the mass in the y direction, if you want to localize it in real space, it will actually also look elliptical. Okay, just you want to localize much less in the light direction compared to the heavy direction. So in real space, you really think about the electron as some kind of elongated object. Okay, and now we're in the liquid phase. We're trying to fit these ellipses together. That's hard to do. They tend to collide with each other. Okay, but if we valley polarize, it's much easier. We all have the same preferred axis, so electrons can actually avoid each other more effectively and gain some potential energy. So ultimately, I believe this is the reason. And this is not unfamiliar. If you try to fit a lot of elongated objects, it's much easier to do if they're all parallel to each other. Okay, so yeah, let me make a couple more comments and I'll conclude. Okay, so first of all, coming back to graphene systems. Okay, graphene systems are also two valley, two spin systems, but they have a different symmetry. Okay, so for instance, the rhombohedral graphene systems that I talked about yesterday, they have a threefold symmetry instead of fourfold. So it turns out one can prove it, Vladimir has actually proved, that if you do the same exercise of correlation energy to second order, or RPA, the preference to spin or valley polarization depends on the symmetry of the system. So we distinguish between two classes of cases. One is that, like in graphene, the two valleys are, the red and the blue valleys are related by time reversal symmetry. Okay, so K goes to minus K, or C2 symmetry. And the other one is like aluminum arsenide, where the two valleys are related by rotational symmetry. Okay, and it turns out that the correlation energy actually has a different preference depending on the symmetry of that relates to values. The time reversal symmetry actually favors spin polarization, valley unpolarized, and for a rotational symmetry, it favors valley polarization, as we saw. Okay, and interestingly, in all these graphene systems, okay, both twisted and untwisted, whenever there's a half metal, there's a state that favors two out of the four flavors, it's always spin polarized, valley unpolarized. In contrast to this aluminum arsenide, which valley polarizes and doesn't spin polarize. Okay, so this is a possible explanation. The other quick comment is about the large RS limit. Okay, so at very large RS, what we expect is the system to crystallize, to form some kind of Wigner crystal. But it's actually an interesting Wigner crystal because we still have the two valleys. We still have the valley degree of freedom. So we can ask, in the Wigner crystal, every electron still has to decide what's its spin and what's its value. Okay, so now for the spin, this is a well-known question, but in the large RS limit, what happens is that the electrons are very far apart. To have any coupling between the spins of the two electrons, they would have to exchange somehow. Either two electrons or multiple electrons would have to exchange. They would have to tunnel over the barrier, the potential barrier that localizes them. And this effect is exponentially small in RS, basically, which is the distance between electrons. In contrast, the interaction between the valley of the two electrons is actually falling off only as a power law, as a function of separation. The reason for that is that it's mediated by the phonons of the Wigner crystal. Okay, so it's related to the mass anisotropy, which couples directly basically to the phonon spectrum of the Wigner crystal. And the acoustic phonons can mediate power law interactions, long-range interactions. So this is a much stronger effect. The coupling between valleys is much stronger than spin. Okay, so if you expand the energy in the large RS limit, lowest order term is just Coulomb, it's one over RS. It turns out that already at the next order, you get this 0-point motion of the phonons of the Wigner crystal, which scales like 1 over RS to the power of 3/3, 3/2. That actually knows about the Valley polarization. So the Valley exchange is of the order of this term. Okay, so it falls off quite slowly compared to the Coulomb term, delta RS. And okay, so A is classical, value independent. The B is value dependent. Okay, and you could try to minimize this energy, this basically this B coefficient, with respect to the Valley polarization of the different electrons, and you get this particular pattern. Okay, so this is actually the minimum energy, not quite what we expected. We were expecting to find just a Valley polarized phase, but it's not. Okay, it's the state where there's a row of the crystal where all the electrons go to this blue Valley, and the next row we go into the orange Valley, which is going to be alternate. Okay, so this state still is not symmetric. Okay, so it breaks rotational symmetry, but not quite a Valley. It's not Valley polarized on average. Okay, so yeah, I'm supposed to do your crystal, and that's basically what I wanted to say. Yeah, so we studied is a 2D electron gas with C4 symmetry, shows that this system actually has a strong tendency to Valley polarize, in addition to aluminum arsenide. Still is a question, why didn't we get quite the right RS? Okay, so when we get close, we become greedy, so we want to get even closer. And we have some ideas of what's missing. And of course, we'd like to apply the same kind of techniques to all these other interesting 2D electron gases we saw. Thank you very much.
One is that the ratio of pictures can be split.
Yes.
Is actually 5 in something exactly ratio of mass. And this is everything. It's the perfect phase, and as it should be ratio of mass. Another comment is related to this radius. Yes. So this is the picture of Weizmann crystal at very large arrays. E is the top of it. He tells us this in our. What happens with Weizmann crystal when it moves closer to transition? So when it moves closer to transition, it loses these square lattice, like gets single very polarized. And actually, lattice is like this, very small distance in this direction, and the ellipsoids are like this. And this is where a transition from linear crystal happens eventually to liquid. So long before the crystal melts, it changes its lattice, becomes single ready, and transitions to liquid appears being single polarized. Let's know this matter. Other questions?
Numbers questions. So if I was to be correctly, there's limited quantum
In the density range where the Valley polarization occurs, there are quantum oscillations at larger densities. Presumably, yeah. So yeah. So right. The most beautiful thing you can learn is you can look at the area of the Fermi surface from the quantum oscillations and compare that to the density. So then, if this phase is indeed the Valley polarized and unpolarized phase, you should be able to infer directly that the area of you should see two degenerate Fermi surfaces. You can't distinguish them, but you should see that the area is half the area that corresponds to the full Lagrange count. Yeah, so that depends on KFL. I don't know exactly what the number KFL is. This kind of exercise.
They did it. They did it for, no, they did it in 2006, but for smaller RS.
Yeah, for smaller arrays. Yeah, so
They
so
see how susceptibility increases.
yes, yeah. So that's true for the relevant RSs. Yeah, I mean, how much lower you would need to go, I don't know. I'll need to try to estimate. Yeah.
From experimental point of view, what they said is don't do quantum acceleration. Just look at the speed as a function of length. Basically, so the full relativization will stop being functional.
Yeah.
And this is how they detect it.
Yeah.
The more
Yeah.
than experiment.
Yeah. I would be satisfied if there was quantum oscillation. So these kind of quantum oscillation experiments were done in the graphene systems. And there you see it beautifully. You see quarter and half metal and full metal.
Another question, have you used the property on this?
Yes.
I guess it would be such. Not easy to do.
Yes. Yeah. We have thought about it a little bit. Yeah. So the phonons of this little crystal is interesting. So this little crystal, you know, if you can do spectroscopy in the right regime, which is leads some probably gigahertz, in this bigger crystal doubles the unit cell, so it has kind of optical phonons with their IR active, so you can excite them.
Which instrumentals to talk about whether this is actually feasible with the model.
Yeah. We've been looking, yeah. So, yeah.
No questions? That's one. You mentioned at one point that in TBT, on the graphene-based system, the half metal state is spin polarized.
Yeah.
What's the key?
Yeah. The key evidence is basically two things. First of all, dependence of the phase diagram in plane field. So you look at the phase transition between a half metal phase and say the symmetric phase. And if it's spin polarized and you apply an in-plane field, the phase diagram should move, the phase boundary between the transition should move linearly in the field. And that's seen. The other more direct evidence now the experiments of spin. So you can apply a small in-plane field, you that polarizes the space, and you actually measure stray magnetic fields with scanning squid at the boundaries, which correspond to spin monetization. You can actually rotate the field and see how the magnetic moment rotates in the field, and it all kind of checks out.
What questions? Yes.
In this version of simulate,
Yes.
And what about before interested in research?
Yeah. So we didn't think about the change. The reason we didn't think about the change is that the change is exponential in RS. So it's actually subleading to any of these effects. Okay, these effects are all coming not from a change; they're coming from the phonons. Yeah, and that induces some kind of power law, long range interaction between values.
Okay, there are no more questions. Thank you very much.
To check the polarization is
Yeah, we'll do that. We'll do. Yeah, we want to do that. Yeah.
yeah, so it would be great.
Yeah.
So there is another transition.
Yeah, there should be another transition. Yeah.
Yeah. And from mine to
and yours is the one that's yours is the one that's
so
experimental.
you can discover two different transitions.
Yeah. I definitely.
Erez, it's good to see you again.
Yeah, good to see you.
I just wanted to say thanks for coming and good to see you.
Yeah. Good. Yeah.
Okay.
Yeah, let's do that. Let's do that. Let's get coffee. everybody, if everything is home is
Yeah.
kind of okay.
Let's talk about a little bit about this.
Yeah.
There's something that we did differently, and I think at one point, let me say a little bit more.
Yeah.
Yeah, sorry.
I just wanted to